This video will explain the PowerPoints that go along with Chapter 2 for Week 1 in MAT095. Chapter 2's focus is on equations and inequalities. In Section 2.1, you will learn about the addition principle of equality. It begins by describing what an equation is. An equation uses an equal sign as compared to an expression, which does not use an equal sign. Equation represents that the side on the left and the side of the right are equivalent to one another. A solution is what makes the equation true. Equations that have exactly the same solution are called equivalent equations. You can find these solutions by solving the equation. The addition principle states if the same number is added to both sides, you're going to have an equivalent value. It's like balancing the equation. For example, if we were to add 5 to both the left and the right side to solve for x, we are balancing out that equation, and x then equals 14, and you can check your solution by replacing 14 in for x and proving that the value on the left equals the value on the right, or 9 is equal to 9 in this case. So if I were to solve a minus 6.2 equals negative 3.5, the first thing I would want to do is get the variable isolated or by itself, and to do that we would have to add 6.2 to both sides so that negative 6.2 plus 6.2 cancels out, and we can solve the solution that a equals 2.7 and check our work. We may be asked in this section if a certain number is a solution of an equation, and in that case all you need to do is replace the variable with the number. In this case you're replacing x with 5 to solve and see if the solution is or is not a solution. In this case it is not, because we end up with negative 6 and that is not equal to 3. You can also find values of the variable that satisfy an equation. And that would be, this is another example of going through to solve for your variable of y and to figure out which values would be equivalent, or y in this case would equal negative 1/5. The second section of Chapter 2 is about the multiplication principle of equality. So instead of adding, we can multiply both sides of an equation, as long as we're not multiplying by 0. So in this case, to solve for w, we would multiply by the reciprocal, or we would flip the fraction. Instead of 1 over 7, 7 over 1. Those would end up canceling out. It would equal 1, because you would get 7 over 7 to solve and get w equals 21. You can also divide both sides of the equal sign as long as you are not dividing by 0. And we would end up by solving an equation with division to get a solution. Here's just one other example, solving with division. So if the variable is being multiplied by a number, to solve for that variable you would need to divide both sides by the number that is being multiplied. So you always use the opposite operation. Again, here is a second example, solving by multiplying by the reciprocal, solving by division. And in this case, you want to get your x isolated. You can subtract like terms. 5x and 8x are like terms because they both have a variable x. So you would subtract the number in front. The coefficient is the term for that. 5 minus 8 would give you negative 3x, and then solve by dividing by negative 3. In section 2.3, they're combining addition and multiplication, so it's a multi-step problem. In this problem, to solve it, we would first add 9 to both sides and then divide both sides by 3. To solve this problem, we would subtract 15 Well, you can go more than one route, but you could subtract 15, or you could subtract 6 from both sides to get the variables on the same side, 9x minus 6x, and then divide both sides by 3. Same here, we would add negative 5 to both sides, or subtract 5 from both sides. It's the same thing. Adding a negative is the same as subtracting. And then we can divide both sides by 6 to solve for C. And in this case, again, we're adding like terms together, simplify the problem, get both like terms on the same side of your equation. You could subtract 11x from both sides, and then you'd have to divide by 4, negative 4, to get a final solution. Then checking your work is your last step. If you have any equations that have parentheses, there are a couple ways that you can remove those parentheses first, so let's go through and discuss the distributive property in order to remove those parentheses. In this case, the negative 6 is on the outside of the parentheses, so you would multiply both of the values inside the parentheses separately by negative 6, and then go through our methods above to solve for our variable. Again, here is a second example where 0.3 is on the outside of the parentheses, so you would want to multiply every value inside the parentheses separately by 0.3, and then the parentheses are gone and you can solve for x. In section 2.4, we're solving values that have fractions. So in this case, if we're solving for a variable a, we can try to get rid of those fractions by multiplying by the reciprocal. Here's another example. By using fractions, solve for x. In this case, we have parentheses, so we would want to distribute or multiply the number outside of the parentheses into the parentheses to get rid of those parentheses first. Keep in mind when you are adding any fractions, we need to have a least common denominator, so you need to find the value of the bottom number that would be the same if we're doing our count bys. So that way we are able to add them together. And then we can simplify our like terms, combining like terms, and getting our variable isolated on one side of our equal sign to solve for x. Again, here is just one more example. So here are some procedures that you can go through to solve equations. Make sure to remove parentheses. If fractions exist, multiply all terms on both sides by the least common denominator of the fractions. Combine like terms. Add or subtract terms on both sides to get the variable isolated. Add or subtract constant values on both sides. Divide both sides by any coefficients. And simplify and check your solution. So here is an example of going through those steps by first removing parentheses, combining like terms, isolating the variable, and checking your solution. In some cases, equations have no solutions, or others may have multiple solutions or infinitely many solutions. Here is an example of an equation that has no solution. You can tell it has no solution if the statement is false. Negative 11 does not equal 3. Here is an example that has an infinite number of solutions. It is always true. In section 2.5, our focus is on formulas. Formulas are used to solve real-life situations. An example of a formula is distance equals rate times time. So using d equals rt, you can use the information from the story problem to replace the variables with our numbers and solve for the missing variable. In this case, you are provided with the distance and the rate, and all you need to do is find the time. Here's another example with solving for a formula using slope-intercept equation form of a line. To solve for a formula, it's the same steps as what we used before. Here's another example. I'm sure you've seen formulas for geometry before to find area of a triangle. Base times height divided by 2 or times 1/2 is the same formula. And then another example for a trapezoid area. Our last section, 2.6, is on solving inequalities. An inequality uses a greater than or less than symbol along with or not including an equal sign to show that the value is either less than or greater than or equal to or less than or equal to a certain value. We can graph inequalities on a number line to show if all numbers are less than or equal to 3. This is what that graph would look like. An open circle shows that that number we're starting at is not included. If this said, on the previous slide, equal to 3, then it is a closed circle is used. So x is only less than, it is not equal to 5, so we use an open circle. So here are just some more examples of how we would graph. If x is less than 4, x is greater than or equal to 3, -1 is less than x, x is less than or equal to -1. We can also translate statements to what the inequality would look like. At least 80%, x is greater than or equal to 80. Fewer than 200, x is less than 200. So solving inequalities, we can multiply or divide both sides by a negative number. So here is an example of solving and graphing an inequality. Again, we're combining like terms. We are also making sure that our variable is on one side of the equation, solving for the variable, and then we can graph it. One more example. And if we continue this, we can see how this equation would be graphed. So the only difference here is we're also adding in what the graph would look like on a number line. Please email me with any questions you have on Chapter 2.